bandits with machine guns on horseback and had to negotiate with them. I was like, okay, I didn't expect that one. But anyway, so that was amongst his many stories. So he definitely got around and loved to travel. But if, without further ado, I probably should introduce our next speaker if he's ready. I don't know, are we gonna go with 40? You have time if you wanna. Are you ready to? I don't want to, yeah, I feel bad, poor Ian. So as you've been told, unfortunately, our first speaker, Mike Davis, had a fall. He's all right, but his talk will be hopefully later this afternoon. And so Ian has graciously volunteered to take over the first talk. And so Ian will be talking to us today. Ian Hambleton will be talking to us today about finite two complexes, Tate cohomology, and four manifolds.
Program. I know something about the work involved in putting on a focus program at this dimension.
Oh, I'm sorry.
I can go to 10 o'clock. Over here. Okay. I think I saw a green light. Yeah. Okay. More audible than before. Also online, if anybody. Great. Okay. I want to repeat what I said inaudibly, which is that I know what's involved in putting on a month-long focus program at the Fields Institute, and the organizers have done a magnificent job. I've been here, throughout, not every day in the month, but throughout various great events here. So, and I really enjoyed this workshop very much. So. A word about Fred, who I didn't have a joint paper with, but we used to have a topology seminar in Ontario, which rotated between Waterloo, McMaster, Western, Toronto. And people from Rochester were regular attendees, John Harper and Joe Neisendorfer and Fred Cohen. So I saw him quite often over the years, and somebody mentioned he was here not a few years ago at the Fields Institute for a meeting. So yes, a wonderful person and a great loss to all of us. Okay. I want to talk to you about a joint project with John Nicholson. Who's in Glasgow. And we got interested in the passage from finite two complexes and smooth four manifolds. One of the early part, I'm going to explain what particular link we're talking about for the connection between finite two complexes and smooth four manifolds. But if you fix a particular fundamental group, G, obviously a finitely presented group, there's a presentation for G, has some generators and some relations. And maybe one of the sort of the key points about finite two complexes is that a finite two complex is essentially an alias for presentation of a finitely presented group. So that's a really, and that indicates, I think it should indicate to anybody who's thought about group presentations that it's extraordinarily difficult, if not impossible, to classify finite two complexes. Or to tell when they're homotopy equivalent, what invariants are there. So, so that's on that side of the correspondence. We're going to have to pick our problem carefully in order to have a chance of saying anything sensible. Yeah, maybe I'll go directly, and yeah, and I will say something about the sort of the before talking about our results, I'm going to say something about the kind of what you might call classical theory associated to finite two complexes. So here's something which is, I'll say one more thing about that. There's something which is between a diagram and a picture. So suppose you fix your fundamental group G. X here is it's a finite two complex. And then there's a minimum Euler characteristic for all possible. This is the minimum of the Euler characteristic of X, where pi1 of X is G. Isomorphic to G, doesn't, if you like. So then you could say, well, all right, I'm just going to enumerate. And we're going to enumerate the finite two complexes at the minimum level. So this will be, is this still visible over here, maybe? It's going to come up. Okay, I'm going to, okay, there's some level here which I can't go beyond. But now at chi-min plus 1, what can you do? You can go from X to X wedge S2. There's another finite two complex. You haven't changed the fundamental group. And if you take any two of these things and you keep adding S2s, there's the famous theorem of J.H.C. Whitehead. I think I'm down below where I ought to be. The famous theorem of J.H.C. Whitehead says eventually they will come together. So that's saying that the theorem says that if X and Y are finite two complexes, this is JHC. It's a theorem. It's a theorem from around 1938 or so, one of his sort of foundational papers, combinatorial group theory. Finite two complex in the same order characteristic. Same fundamental group. And he says you can specify the isomorphism of the fundamental group if you like, and then there exists an R, so that X wedge R S2 is homotopy equivalent to this, and you even get a homotopy equivalence where H star is given by alpha on pi1. And you can even get simple homotopy equivalence. So, after you stabilize with these S2s, then everything collapses in the strongest possible sense. We're going to, in this talk, so this is, you might ask, well, how many copies of S2 do you need if you have the group? That's a fundamental question not solved. My collaborator, John Nicholson, has a nice paper where he shows that in the realm of certain families of infinite groups, finitely presented infinite groups, you can have arbitrarily large times before you stabilize, before they come together in the sense of J.H.C. Whitehead. In this talk, we're going to specialize to, so I'm going to assume that G is a finite group. Where there's a nice result from the 70s, the 80s, Dyer-Zaradsky, with Browning. Anyway, the nice result for finite groups is, I could reproduce a little bit of that. Here's the chi-min level again. And what happens here is in the very next level, everything collapses to 1. So this is as I should have put this. I should mention West Browning. They got the homotopy equivalence part. I have a little paper where I added the simple homotopy equivalence part. So after one more, after chi-min plus 1, everything collapses. Okay, so that focuses attention, I think, on something you might call HT min of G, which is going to be just a set of finite two complexes X with chi1 of X equals G and chi of X equals chi min. If I ever need a notation like that, then there it is. So that's. No, we want to focus on the bottom level. So that's where that's where if I have two finite two complexes, the mystery is, are they homotopy equivalent or not? And so we focus on the bottom level. And there it's there are three famous preprints by West Browning from the late 70s, where he gives an algebraic description of a group which should classify these ones, but it's pretty hard to compute. And maybe I should say the great success of for finite groups for classifying finite two complex is the case where G is finite abelian. And this is going to be the case that's actually quite important for the work in our talk. This is Wolfgang Maxler introduced something which is called bias invariant, which completely classifies finite two complexes at the minimal Euler characteristic up to homotopy equivalence. Actually, I think it even does simple homotopy equivalence. The paper that if you ever want to look at this, I think this was in the 90s somewhere. The summary paper, which goes into all aspects of this, is by Peter Linnell. A beautiful paper. Okay, so what I want to do, I'm going to describe the biasing invariant in detail a little bit later. Maybe just for the moment, it's an invariant which is defined more generally than for finite abelian groups. It just happens to really work well for finite abelian. And it's an invariant which weakens homotopy equivalence to homology equivalence, integral homology equivalence. Okay, so you can imagine that that might be easier to compute, and when it works, it works. All right, so the next thing I want to do is to tell you which particular way we're talking about getting from finite two complexes to smooth four manifolds. Okay, so this is there are more than one way to say this construction. The easiest way is to say the easiest way is to say thicken. If you have a finite two complex, and again, I'm going to reserve the letter x's and y's for these finite two complexes. And I don't have to have finite fundamental group for this, but general position, this I better remember this. You can put it in R5 by general position, and then you can take inside of R5, you can take a regular neighborhood. Okay, so even though this is just a finite complex, once you've gone to a regular neighborhood, you have a smooth, compact four manifold with boundary. And the particular smooth four manifold we want to talk about is the boundary of a thickening. Okay. So this is here. This is a smooth, closed four manifold as the boundary of a compact, smooth four manifold. Okay. Yes. Thank you. This one's 4. This is a 5 minute. Yeah. Okay. Right. Okay, so that's the construction we're talking about. We're going to go from x's to m of x's. And of course, you might wonder, well, how well defined is such a thing? It's not too bad. For example, if x is homotopy equivalent to y, again, finite two complexes, then m of x is h coordinate to m of y. And the idea is very easy, that you simply you have x, and this might be a picture of n of x in R5, and then inside here you can throw in n of y, and if you have a homotopy equivalence, then the region in between will give you the h cobordism between the boundaries. If you like, if you put s here for simple homotopy equivalence, then you can upgrade this to s cobordism. Right. Now, in high dimensions, maybe I ought to say there is a high dimensional analog of this story, but I'm not going to talk about today, but is in our paper. In dimension 4, this, you don't know how to go beyond this because there's no, well, the h cobordism theorem is false for 4 manifolds. So that's, but still, this is the h cobordism. That in particular implies that m of x is homotopy equivalent to m of y. So this is there's a homotopy theory question here, which is, what information do you lose if you start with homotopy types, or gain, start with homotopy types of finite two complexes, do this thickening construction, and the resulting things. What can you say about the homotopy type on this side? So questions, I guess. This is the hard question, I guess I should say, was that if, I'll just record it here, if this is does this imply that m of x is diffeo to m of y? That would, if you have to, somehow could one overcome the h cobordism problem and actually prove a diffeomorphism statement. And here I might mention that for these particular kinds of thickened manifolds, the invariants that gauge theory has been so successful in using to distinguish smooth 4 manifolds don't work at all. The Farber-Witten invariants vanish for these kind of manifolds. This is recent work, so Farber-Witten. This is a recent paper by Mike Friedman, Slava Krushkal, and Ty Lidman. All right, so we're not going to do the hard question today. The not so hard question, or well, this, I would say that's impossible. We're going to try something easier. So if you start out with 2 homotopy inequivalent complexes, can we decide if m of x, or is, well, maybe I should just express it as a hope. Does that imply that m of x is not homotopy equivalent to m of y? So I think homotopy equivalent. So starting with homotopy inequivalent input, do you get homotopy inequivalent output? Does it survive this thickening procedure? And when I say it like that, there are probably obvious counterexamples, but let's move on. This is the question we want to study. And the rough outline of what we want to do, what we have done in our paper, is to start with the bias invariant and define something called the quadratic bias invariant, which can measure this homotopy equivalence problem on the thickenings. And before I get into that, I want to make one remark. So in other words, on this side, you can say, do there exist, this is another question, homotopy inequivalent, maybe I'll try to write it more with more symbols, four manifolds. Smooth four manifolds which are not homotopy equivalent and but stably diffeomorphic. So this gives me the chance to introduce the four manifold version of the stabilization that J.H.C. Whitehead is using, namely, just in other words, does there exist an R? Let's put chi then. Chi then. Does there exist an R? And just for reassurance, well, that's going to follow same fundamental group. Does there exist an R such that M connected sum R S2 cross S2s is diffeomorphic to N? So this is the definition of stably diffeomorphic when you start it with two things that have the same Euler characteristic. And just a little remark. To know if pi 1 of M is trivial. So if you start with simply connected smooth four manifold, which has been, of course, the focus of so much energy and attention in smooth four manifolds, you can't have examples like this. And the little argument feeds in at some point Donaldson's Fields medal to and the classification of unimodular symmetric bilinear forms over the integers, simply because in the simply connected case, because in the simply connected case, the homotopy type of a smooth four manifold is entirely determined by its intersection form, the ordinary intersection, and W2 information. Yeah.
Which four manifolds are M of X's?
Yeah, that's okay. It's I'm not even sure how to parse that question. For us, they are the thickenings of finite two complexes. So that's clearly not an answer that we'd be happy with. I don't know how to distinguish them. If somebody hands me a smooth four manifold in the world, I don't know how to tell whether it's diffeomorphic to an M of X. But then I'm not alone in that. Nobody does. Yeah, I'm going to try. Yeah. Okay, so here's the. Okay. Yeah, so what I wanted to say just to finish this discussion is that there are no examples of this sort for simply connected smooth four manifolds. And the work, a generalization of the bias invariant to something we're calling the quadratic bias invariant, is based on foundational ideas of Matthias Kreck and Jim Schaefer. So they have this fantastic paper from 1984, which gives the first examples of, and then necessarily non-simply connected four manifolds, which are of this type. They're not homotopy equivalent. They're stably diffeomorphic. They have the same fundamental group. And the Kreck-Schaefer, they got some. There exist examples, and the pi 1 in this case for them. This was the smallest pi 1 that works in their examples, but they do have an infinite family of pairs of examples giving smooth four manifolds, which are not homotopy equivalent, but are stably diffeomorphic. You notice that those are that's a finite abelian group, and the homotopy part of the classification in particular, distinguishing the finite two complexes with this finite fundamental group is an application of Metzler's bias invariant. The right. Yeah, okay. So I'm now going to, I'm going to try to outline the route that we followed, first of all, in spending close to 2 years reading and understanding eventually the correct Schaefer paper, trying to unravel some of the great ideas that are in there, and then to see if we could push it through more general fundamental groups. An essential feature of the eventual reduction they do is that they're working with elementary abelian groups of odd order. In fact, in general, the primes have to be congruent to 1 mod 4, but these are for sort of internal reasons that have to do with the eventual calculation. Maybe one more remark about to relate these two sides. So this is the passage I want to talk about. X goes to m of x. And just to say, before it passes us by, that the Whitehead stabilization operation for two complexes, wedging on a two sphere, after you feed it into a thickening, gives you a stabilization by S2 cross S2. So one can see S2 cross S2 with its wedge of two spheres sitting there, and that's so the two stabilization operations are compatible, if you like. Excuse me. Well, there's even one more parallel thing, I guess I could say. Where's my tree or their tree? For the two complexes, after you do one stabilization, everything comes together. And for four manifolds, Matthias and I proved that, at least in the topological category with finite fundamental group oriented, that one stabilization by S2 cross S2 is enough. In other words, if you have stably diffeomorphic topological closed topological four manifolds with finite fundamental group, after adding on one, and then it's enough to add just one S2 cross S2. That same question in the smooth category is wide open and a focus of much interest in the field. But okay, so these are kind of the analogies, I guess, that I wanted to point out between two complexes and four manifolds. And now I think it better be the time to give you a quick definition of the bias invariant, and then tell you where Tate cohomology comes into this story. Happy to, of course, be interrupted at any time. Or corrected, I guess I should say, at any time. Maybe I'm going to leave that. I like that picture. I'm going to leave that up on the board. I'm not going to put too much over here, except maybe a very quick indication of how you define the bias invariant. This is a good place for me to write something that I was intending to write before, and that is that if you take, if you look at the minimal, this number chi min of G, then it's it's less than or equal to 1 minus the deficiency. This is a concept you probably have encountered in group theory. This is a maximum over D minus maybe I'm calling it S over all presentations. You fix your group and you have these presentations. If we were to specialize to, well, you see this is just the Euler characteristic, the number of generators minus the number of relations. This is extremely difficult to calculate. It's very interesting to see finite groups which have deficiency 0. And that's a part of a story which Alejandro and I investigated in wondering about, once you fix a finite fundamental group, what's the minimal Euler characteristic for a smooth four manifold that you can have? And this enters into it, but right. The bias invariant. All right. So this is based on a sort of a foundational lemma in homological algebra, which is suppose I had x and y again, and let's have the Euler characteristic the same. And for this to get even off the ground, they're going to have to be minimal. And there's one more condition I'll tell you in just a few moments. And of course, the same fundamental group. Maybe this is the reason I introduced this term, this notation for HT min, but I could just say that more quickly. So what can you do? What can you do with this? Well, you can take the chain complex of the universal cover. Augmented with Z. And then up here, I'm not just saying that they're equal, I'm fixing an isomorphism. So we're going to work with the two chain complexes are, which you might call polarized, meaning that these are ZG. This is G. These are ZG free chain complexes. Right? The universal cover. What does homological algebra tell you can do here? Is if you start with the identity here, it tells you that you can find a chain map. Let's call this H. Now, that chain map is not going to be a chain. I mean, we're starting with homotopy inequivalent chain complexes here, so we're not expecting this to be a chain homotopy equivalence. However, if you pass to the map on integral homology, so this thing is, this is well defined up to chain homotopy equivalence, the lifting that you get. Sorry, getting low here. I want to write one more thing under here. If you pass to, if you look at the map on H2, so H0 of this H is just the identity. If you pass to the map on H2, integral homology H2, I said the bias has to do with integral homology equivalences, then you get a map from H2 of X and the great thing about this map is that it has that these things are both free abelian groups of the same rank by the Euler characteristic assumption. And the great thing about this thing is it has a determinant of this H2 of H in Z mod M units, where M, this is a really important number for this problem. Maybe I can help to explain this a little bit better by saying that from pi 2, you can come down to H2 of X, and you can also then come down to H2 of G by using the classifying map of the universal cover. So I should put Y here, shouldn't I? H2 of any of H2. So this map descends here, and then when you come down to H2 of G, you get the identity on H2 of G. All right, so what's important here is the structure of H2 of G. Okay, well, it's a finite abelian group, and you can write it as Z mod M1 mod M maybe T. And the usual canonical way to do this is to take each one dividing the next one so that you get a unique decomposition. And the M in this thing, M sub G is the smallest one in this thing. The GCD of all the cyclic orders of that. Okay, so that's a first of all, a homological algebra fact that you get this thing. And the second thing, the second part of it is that when you have a map of free abelian groups with the same co-kernel, then with inducing an isomorphism on the co-kernel, then you get the determinant. You measure that by a determinant in this lowest exponent. Okay, there's a little bit of indeterminacy here. Namely, you could divide by, say, automorphisms of z to the d, and then what you want to do is to divide by plus or minus 1 here. And so the bias invariant, let's call it d of the bias invariant for x, x comma y, it's expressed at the moment as a relative invariant, is an element in z mod m units divided by plus or minus 1, and also by something called d of g, where d of g is equal to the image of a homomorphism from automorphisms of g into z mod m. So in order to do this, we polarize the fundamental group, and then you have to divide out by the automorphisms of the fundamental group to get something well defined. Okay, that's the bias invariant, roughly. It's not going to tell you much if this M0, this M1 is, well, it's not going to tell you much if these ranks are not the same. So there's a condition, which is that G should be efficient. And a condition for the bias invariant to even potentially tell you anything is that G should have an efficient presentation, and that is that the Euler characteristic should be equal to 1 plus the minimal number of generators in H2 of G. Let's for magnitude. Yes.
Thank you. I'm Peter Webb. Just to clarify in my mind, where you've got pi to x, pi to y on the left there, are they in fact the relation modules associated to some presentations that you might get from the complexes?
No, the relation module thing would occur here.
Is it?
This is just a single thing, and then there's the generators, and here are the relations here. But this thing is what's called the third Heller shift.
So C1 it looks like a copy of the single group ring. No, maybe C0 does.
C0 is a copy of the single group.
Okay,
one zero cell, a bunch of one cells, making your yeah.
Thank you. Yes.
Is that clear enough? Okay. Now. Okay. Oh yes, I did want to say that as phrase, this is looking like a relative invariant. You can make it into an absolute invariant by fixing some reference to complex with the minimal Euler characteristic, and then comparing to that. And then you have to prove that with this indeterminacy, you still get a well-defined invariant. So it's better actually to regard the bias invariant as a single invariant of a finite two complex into this same group. Okay. Now I want to now, since yes.
Yeah. Is the bias invariant, you've just told us where it lives? Is
Yes.
it this determinant, or
Is it
I'm
what?
confused? Are you that you told us where the bias invariant
It's the
lives?
determinant of that
It's the
map.
determinant. Okay,
Yes.
thanks.
Right. Yeah. Well. Thank you. I'm erasing the very thing I probably want to talk to you about, but I have to tell you more about the algebraic topology of the thickenings in order to now we want to talk about I want to talk about the quadratic bias invariant. But first, let's have thanks to Peter's question, let's have a little interlude about the structure of this module, and that is we're going to use Tate cohomology, and in particular, I'm going to use Tate H0 with coefficients in let's just say generally for a moment. So this L, this is a ZG module, and I think it's just a ZG module. The first instant EG L is going to be pi2 of x, okay, which is of course free as an abelian group. It's a very interesting ZG module. Very difficult to understand actually, but the definition-wise, what are we looking at? We're looking at the fixed submodule. That's what L upper G means, divided by norms. So we're just looking at you have the norm map, which is the sum of the group elements, and you can divide out by the sum of the group elements in L that lands in the fixed set, but there's something left over. And e.g., for example, if L is equal to Z, you get Z modulo the order of G. Okay. So I guess I'm assuming that people are comfortable with Tate cohomology in various dimensions. And the thing I wanted to point out is that if you look at a Tate H0 of G with coefficients in pi2 of x, what is that? Well, this thing, there's the technique. So Tate cohomology is very nice with short exact sequences, and if you follow down through this resolution, this exact sequence, you're encountering free modules every second step. And the Tate cohomology, when you plug in a free module, is 0 for a finite group. And this then gives you, well, it gives you Tate H minus 3 of Z. You shift down, but by Tate duality, we have our friend H lower 2. So this is a key connection between the two complex business and the next part. Okay, so Tate duality gives you cohomology in negative dimensions, gives you homology, and then there's a bit of a shift. Right? All right, that's yes, right. Okay. I think I may just have time to tell you what the quadratic bias invariant is, and then to tell you our results without telling you a proof of anything. Okay, I want to tell you a little bit about M of x. We should look at the universal cover, and this is a closed smooth four manifold. So let's look at the universal cover with integral coefficients. And in particular, we also want to look at the intersection form. Maybe let's call this S of mx, x tilde. So the equivariant intersection form on a smooth four manifold, the universal cover, the best place to have it land is in the integral group ring, which sometimes we call lambda. I don't think I need this notation in this talk, but I'm about fixation on calling this group ring lambda. At any rate, these are, of course, these are ZG modules. So first of all, so what can one say for these thickenings? What does it look like? Well, it looks like this. And then here is some I think I'm going to call this phi. And what so this is on, and it's on h2 of m of x tilde, which is, as a ZG module, it is pi2 of x plus pi2 of x. The two summons where the star means the dual, the Hom dual, either into Z or into lambda. It's your choice. It's the same. So this describes exactly the module. And you notice that because these things are dual, there's a possibility of doing an evaluation. So that's what, in the order of sum ends, this is the pi2 star part. And this is the pi2 part. So you have the possibility of doing an evaluation and then dualizing that to do the other part. So this is a symmetric Hermitian form over the group ring. Now there's one more. So these are modules. This is the yeah. So these are interesting modules. And the extra thing to note is you're one basis change away from, you can assume that phi upper G is 0. Phi is, this is the pi2 of x part, so it's a form on pi2 of x. And when I say phi upper G is 0, I mean that form vanishes when we restrict to the fixed set of pi2 of x. In terms of the L up there, if you restrict to L upper G, the numerator there and the Tate cohomology thing, then you get 0. All right, so what's the punchline of this is that, and this was the, I think, wonderful idea of Craig and Schaefer. Let's look at this form on Tate cohomology. I have a non-singular Hermitian form on these modules. What if I just apply Tate H0 to this form? What do I get? All right, so that's, I think I might need those things. Okay, so we're going to look at two forms. There's the form that we're going to call E upper G, and this is the form on L upper G star plus L upper G. And I think I can, yes, it's important to have those things. This thing has the form, and this has some beta ones. What are these betas, you ask? It has to do with, where's the right map? What are these betas? Oh, yes. It has to do with looking at this. If you take L is pi2 of x. Okay, so then you look at this sequence, which is L star upper G into LG upper star. And then here you get these things. And the betas themselves, these beta i's, are just the order of G divided by the mi's that are in the decomposition of H2 of G. Okay, so what you notice about this thing is that this is, I haven't done Tate yet. This is just the fixed form. Because of the 0 on the fixed set of this form in the corner, the lower corner, this is it looks like a hyperbolic form, except that it's scaled hyperbolic because these betas are not all the same. There could be groups of them that are the same. Okay, and now we're going to do E hat of G. And this is going to go on to E hat, L hat star plus L hat. And what's it, it's on, I wrote equals here, but this is the underlying module of this form here. Do that. Lo and behold, it looks the same. Except now this is a form on a finite module. It's this where this L hat is Tate H0 of G with coefficients in pi2 of x. And the star is like the dual for finite abelian groups. You HOM into Z mod the order of the group. Okay. There's a natural passage from one of these things to the other. And okay, so time is moving on. So let me say that the bias invariant gives you a diagonal isometry of this form. So the bias invariant was a determinant, and it was a determinant, after you make it absolute, it was a determinant on a map on L, this thing, on pi2 of x. And when you take, and it's the determinant was relatively prime to the order of the group. So if you make a, so let's say the bias invariant of x, this is now the absolute version, is in wherever, and then some automorphisms. So this gives you an element, this gives you a diagonal isometry of let me call this something. I'll call this alpha. Alphas and betas is a diagonal isometry of E hat G, and what the, so remembering that this is the star corner and this is this corner, to get it from an automorphism there, you can do alpha star inverse plus alpha in the diagonal isometries of E, G hat. So that, in essence, is how you pass from the bias invariant, which is going to distinguish, hopefully, finite two complexes, to something which, hopefully, will distinguish the four manifolds up to homotopy equivalence. The passage is, so, and this thing is what we when we formalize it properly, this is going to be the quadratic bias invariant. But so this just tells you how to get into an isometry of this form. Defining invariance is all about indeterminacy. Right? Now, in the linear part here, there's very little indeterminacy, just coming from automorphisms with determinant plus or minus one, and some messing around with the automorphisms of the group. But here we have to divide out by the things that lift to that. All right, so now I think that in these last few minutes, I'll just tell you what our results are. I hope that and maybe try to say that the main work for us was to find the right indeterminacy setting for this invariant, and then to compute it in some cases, which led to more examples. That's sort of the short version of what the results are going to be. But I guess I do want to point out that isometries of hyperbolic forms, that's the subject of odd dimensional L theory, surgery obstruction groups. So SUN of lambda is by definition the automorphism groups of a standard hyperbolic form. When you have scaled hyperbolic forms like this, I think that's a kind of totally unknown algebra, that at least as far as I'm aware. So it could be worth investigating. Wallin, back in the 60s, had some papers about quadratic forms on finite groups, but he doesn't discuss automorphisms in those papers. All right, here are the summary results of our. So there's all of these things are joint with John Nicholson, and maybe this with the paper's on the archive just at the beginning of this year, but of course it was done a little earlier. Maybe just to give you an inkling of where the, okay, I'll do this after writing the first theorem. So the first theorem just says we have an invariant and then leaves open the question of what's it good for. And the first theorem says that if the quadratic bias invariant defines a map beta q for quadratic from a collection of an obstruction group, okay, such that if m of x is homotopic to my, and that tells you that their quadratic bias invariants are the same. Okay, so there's a theorem almost without content except to tell you what M4 of G is. This is going to be the set of doubles. And in HT min, there's no point in looking at them in the larger Euler characteristics. So, okay, just formulation. This just one indication of the work that goes into defining this for all finite groups, not just finite abelian ones or other ones. The indication is that the obstruction group, so this BQ of G, I do feel tempted to write put on some symbols on the board. There's a polarized, before you divide out by the automorphisms, there's a polarized version. So where you take the diagonal isometries of E hat of G, and I think I told you how to get into there. The whole problem is the indeterminacy. So there's the images of the isometries of E upper G. And then here's the tricky term is intersecting diagonal isometry. Okay, this is a complicated looking expression, but what we're doing is relatively simple-minded. As I said, we have to divide out by the isometries of the upper form. That's this part. But then there's the choice of that lifting in homological algebra, lifting that map. How well defined is that? And that can lead to things which are upper triangular. That's what tri stands for. And then in the end, of course, you have to land back in the diagonal isometries of E hat after you push everything down, and that's the denominator. So it's a kind of and in general, horrendous to compute. So this second and third were just the applications. And of course, with applications, you get assumptions. So here's a theorem 2. It's the same group here. If G is finite, and here's the main simplifying assumption is that this is a from m greater than or equal to 1, is that the H2 of G, instead of having, oh, it has disappeared, but instead of having a lot of cyclic groups of different orders, it is in some sense elementary. It's the direct product of the same cyclic group again and again. The implication being that in this algebra, those betas will all be the same, so that up to a single scaling, it's a hyperbolic form. Right? And now we're back to more familiar algebra. So that's the need one. And G has an efficient presentation. I think I'd find that. Then BQ of G is going to look startlingly like the obstruction group for the bias invariant, with one hardly noticeable but important distinction. So taking advantage of the simplification of the going back to actual isometries of a scaled hyperbolic, the influence of the ones up above here, where they are, the ones that coming from the upper form is to divide it by squares. It looks like a little thing, but anyway, it was take some time. And this is the action of the automorphism group. Okay, and finally, theorem 3. So given for each k greater than or equal to 2, there exists finite group G and closed smooth for manifolds. I think if M1 up to MK, such that MI pairwise not homotopy equivalent, and all stably, if maybe I should say same Euler characteristic. All stably diffeomorphic. Okay, so in other words, the end result of going to a bit more general setting than was the original work of Kreck and Schaefer is that we produce arbitrarily large families of group smooth form manifolds, which are homotopically distinct, but then collapse after the stable diffeomorphism. This is a question we was asked. There's Daniel Kasprowski and some co-authors have a nice survey of examples and counterexamples in 4-dimensional topological manifolds. And one of the questions they asked was this. One more remark, which we liked, I have to tell you, is that the bias invariant is, I told you, is very good at distinguishing finite abelian fundamental groups for 2 complexes. Apart from some periodic groups where it follows for other reasons, there were no other examples of finite groups where the 2 complexes were distinguished by the bias invariant. But we found a family, and here's the fundamental group. This is the last thing I'm going to say. I know. Everybody likes Q8 though. So P. Right. That's it.
Any questions for the